Video Lecture 2.5, Net Radiation. Just like an accountant views the world as debits and credits, a business person, assets and liabilities, a consumer, a deposit or a withdrawal, we've got inputs and outputs. And so net radiation is a measurement at the top of Earth's atmosphere, at the top of the troposphere, which measures the relationship between the incoming solar radiation, the inputs, but then also the outgoing long-wave outputs. And so once again, it's a measurement that's done at the top of the atmosphere. And so it measures what's coming in, but it also measures what's going out. Outputs. What do I mean by long-wave outputs? We've already talked about this in previous video lectures, but we can think of outputs as reflection by clouds. Aerosols. Think of aerosols as pollution, both natural and man-made or human-caused, but also Earth's surface, like we just talked about with albedo. Also, thermal radiation or long-wave radiation, that long-wave infrared, we also refer to that as heat. So essentially, if all things being equal, global net radiation for each year should equal 0, thinking about inputs and outputs, the same amount coming in as going out. If not, then global temperatures must be either rising or falling accordingly. Once again, working with the idea that we're building and building and building on topics throughout the semester, the imbalance in net radiation drives global circulation patterns, which is one of the next topics we're going to hit, climate and weather, which will soon after that hit, and then, of course, vegetation, the characteristics we find actually on the ground. What we're going to be looking at is a series of maps that showcase net radiation for March, June, September, and December, and these are produced by NASA. What we have here is places that have a high positive net radiation would be red, so that means they have more incoming than outgoing. And places that are blue-green are going to have a negative net radiation, so they have more outputs or more outgoing than incoming. Places that are essentially, a balance, same coming in as going out, are going to be that yellowish color. Two things to note is the general position of these colors throughout the seasons, how they change, why they change, but also the Sahara Desert. Pay attention to the Sahara Desert and kind of areas around that. And why does the Sahara Desert kind of remain the same throughout the year? So these are kind of some things I want you to think about critically as we go through these series of maps. Taking what we just learned on the previous series of maps, between the tropics you're going to have energy surpluses. So here, shortwave incoming is greater than the long wave outgoing. Key to understanding this is things we've already talked about, but the sun's declination pretty much always nearby, and they also have that consistent day length, 12-hour day, 12-hour night. The opposite would be true for our polar regions. Those are going to be areas that these energy deficits prevail. And so here, once again, long wave is going to be greater. There's going to be more outputs than inputs. And so understanding this, of course, we've got the situation of the sun's declination where we have 6 months of absolutely no incoming solar radiation compared to other areas like we've seen in the tropics. Of course, another characteristic, as we learned in video lecture 2.4, is albedo, lighter surfaces. The snow and the ice found in polar regions is going to also create a situation where we have more reflectivity, more long wave radiation. Finally, where we are, roughly, this is the first time we've come across this term, the mid-latitudes, but we're going to come back to it time and time again. This is where we're going to find a general balance between energy gain and loss throughout the year. And so that's pretty much where we are. We're going to have, at times, a positive net radiation. At times, we're going to be exactly 0 or even. But then other times, we'll have a negative. And that's very much related to seasonality.